Hello everyone, I'm Jane Dai from the University of Hong Kong. Thanks very much first to the conference organizers for organizing this very wonderful program and asking me to give a talk on the accretion aspects of the TDEs. So as people have been mentioning since yesterday, there are lots of interesting accretion and outflow and jet physics that we can learn from TDEs. And in this talk, I'm going to particularly focus on that aspect that we can expect to have super-Eddington accretion in a lot of TDEs. And this super-Eddington accretion physics can be used to apply to other black hole systems undergoing super-Eddington accretion, like URX, and also especially high redshift quasars. And we have been starting to observe them with super-Eddington luminosity using JWST. So just to start off this talk with a little bit of theoretical background of super-Eddington accretion. So we expect this accretion flow structure and geometry in super-Eddington accretion to be rather different from the standard thin disk picture. In particular, the large radiation pressure is going to puff up the disk to be geometrically thick. And also this radiation pressure and also added with magnetic fields, they can drive a lot of very powerful winds, and also we expect the radiation to be not leaking out very efficiently in the systems because of the photon trapping effect in the inner disk. So in order to study this kind of accretion structures in details, and especially to apply them to TDEs, we have been carrying out simulations using a code called HAMRED, which is a 3D Fuji-R radiation MHD code. I'm not going into a lot of details, technical details about the code, but just to mention that we have to evolve radiation simultaneously with the gas for this type of accretion because the radiation can affect the dynamics of the gas a lot. And we try to resolve a lot of rate transfer physics in the code using the M1 closure. To apply them onto TDEs, we put the accretion flow around black holes with relatively smaller masses. We have a lined disk here, and in particular in the later study here, I want to mention is my student Tom Kwan, a PhD student who has been running simulations sampling different accretion rates. And the reason we want to do these simulations at different Eddington ratios is because we want to use them to study the evolution of TDEs. And here, because this evolution in TDEs lasts for years of time scales, so it's impossible to resolve that whole evolution using one simulation. So the method we adopt here is to do simulations at different Eddington ratios which resemble different epochs of the time evolution of a single TDE. And we sample the rates from a few Eddington to a few tens of Eddington accretion rates. And also let's remind ourselves that for different TDEs, depending on the stellar and black hole parameters, so the peak of the TDE can also have different Eddington ratios, and therefore we can also use these TDEs, these different accretions to understand different TDEs at peak. Okay, so here let me introduce the basic structure of the simulated accretion flows. So we find that this kind of disk funnel geometry structure to be rather ubiquitous in all super-Eddington accretion. Right, so basically, as mentioned, we have this geometrically and optically thick disk, and above the disk, covering a lot of solid angles, we have a lot of optically thick winds. And this wind has a slower component and a faster component, which is called ultra-fast outflows with speeds faster than 10% of the speed of light. And these both types of components have been observed from TDEs and other super-Eddington sources. Around the polar axis, there can be optically thin region, which we can call super-Eddington funnel, and we can expect the direct emission from the disk can leak out easily from this funnel region. And also this wind produced by super-Eddington accretion can be very powerful and massive. And people might think this is not very important in terms of the feedback to the galaxy, but actually we have been studying some TDE relation with the growth of massive black holes through analyzing some previous cosmological simulations. So this is a particular simulation run using the Ramses code by collaborators. and which was run from redshift roughly 11 to 5.7. So we took a look at some zoomed-in regions for which we can resolve the galaxy stellar density profile rather well, and we can calculate the TDE rate based on that. So what is shown here in the red panel is the percentage of the black hole mass gained through accreting stars, through TDEs, as compared to the total, which is accreting stars plus accreting gas. And you can see at high redshift, especially when these black holes are still in the intermediate mass black hole range, they can actually accumulate a significant fraction of their masses through TDEs, which is to say, it's possible MBH have grown significantly through TDEs at high redshift, especially when there are mergers happening. And also in this space, the super Eddington accretion feedback from TDEs, like through these powerful winds or radiation or jets when it's produced, can be very important for the growth of the host galaxies as well. So I think that's something worth further investigations. Okay, so back to the super Eddington accretion simulations themselves. So here we show this vertical structure of the accretion flow at different accretion rates. So as you can see, the structure stays very stable despite the Eddington ratios vary from a few to a few tens of Eddington accretion rates. And as this accretion rate increases, the difference between them is that the outflow to inflow ratio would increase, which means if it's at a higher accretion rate, more of these fallback materials will become winds. And of course, the wind density also increases with the accretion rate. And also at higher Eddington ratio, the wind velocity actually decreases very slightly. I think this is because of the mass loading of the wind, but this effect is quite second order. Okay, and we can also take a look at the photospheres in these accretion flows. So what's plotted here is the black line is the tau equals to 1 photosphere for electron scattering. So it's optically thick here and optically thin there. And this red line is the effective absorption photosphere, considering free only. So we can see that in a lot of this dense wind and disk region, the scattering photosphere is the largest, and that scattering opacity dominates. So along this direction, the physics is basically consistent with this 1D model proposed by collaborator Nathan Roth, in which you can see the electron scattering photosphere is the largest one here, and all these continuum and line photospheres are embedded within the scattering photosphere. So the meshes there like to have this kind of geometry. The importance is that means a lot of the lines we see in TDEs are actually broadened by this scattering optical depths instead of kinematics. Right, and then if we look at different Eddington ratios, we can see this scattering photosphere as the wind density becomes denser and denser. They would also, basically this funnel would close up near the pole. So this leads us to propose this unified picture for TDEs, which is if we look at a fixed Eddington ratio, say around tens, then there is this funnel region near the pole. Looking down the funnel, we can see the X-ray emission from the disk, and then we would expect more and more reprocessing to happen in the wind and disk region, and we can potentially see a lot of reprocessed optical and UV emissions from side. And when the Eddington ratio is lower, which corresponds to, say, later time in TDEs, then this funnel can effectively open up. We see more X-rays leak out in this case. So to quantitatively confirm this proposal, we further carried out post-processing of the simulated accretion flow using a code called Sedona, which is developed by collaborators Dan Kaysen and Nathan Roth. So Sedona is a Monte Carlo radiative transfer code involving non-LTE equations. I won't mention a lot of details here again, but just to say that what's so special about it is it can resolve this bound-free and bound absorption and emission physics in the scattering-dominated regime. So I think here this allows us to obtain very reliable spectrum from super Eddington accretion flows. So in particular, we did 1D post-processing, which means we divided this accretion flow into different inclination bins. We did averaging in each bin, and we injected black body emission around the disk temperature to the 6 Kelvin from the center, and let it propagate and have all this radiative transfer in the accretion flow until it leaves and escapes the photosphere. And I want to mention in the later study, this post-processing radiative transfer calculation is carried out by PhD student Lars Thompson. So let's take a look at the spectrum produced. So when we fix the accretion rate and look at different viewing angles, so this is the spectrum we see going from the polar direction to the disk direction. So we can see that indeed along the polar directions, the X-rays can leak out. And as we go into larger inclinations, in the faster wind, we see a lot of adiabatic reprocessing. And in the slower wind and the disk region, we see a lot of photonization and line reprocessing. And that is heavily reprocessing the X-rays into mostly UV and optical at larger inclinations. And apart from this viewing angle dependence, we can also check how the spectrum evolves as the accretion rate changes. So here the idea is like for a fixed TDE system, we assume there is not much precession going on of the disk. So we are mostly looking at the disk along a constant viewing angle. So let's say if we look at the disk from face on and change the accretion rate, and we can see basically the funnel is always there in this setup, and we mostly see X-rays leak out no matter what is the accretion rate. And then if we look at it from edge on, there is always a lot of materials to reprocess the disk emission. So we are basically always seeing optically strong events. And the evolution really happens from intermediate viewing angles. So here, for example, if we go from 24 to 7 m dot Eddington, we can see initially at higher accretion rate that wind is more optically thick. So a lot of the X-rays are reprocessed into UV optical, and at a later time, the wind becomes more dilute, the funnel opens up, and we see X-rays leaking out. So I think this quantitatively confirms this dynamic unification model that we proposed. Right, and also we did a lot of fitting between this modeled results and the parameters that we can resolve from TDE observations. And in particular in optical bands, like if you look at this optically strong spectrum, we fitted, like if we take this, basically this slope in the UV optical range, and we fit that to a black body emission, we can see that the temperature fit is always around 10 to the 4 Kelvin, and is very consistent no matter what it is, the viewing angle or the accretion rate. So we think that is quite consistent with what's observed in TDEs. As its luminosity, optical luminosity drops by 1 or 2 orders of magnitude, the temperature stays basically constant, maybe with a slight increase or decrease. The effective radius is also quite consistent, and also quite interestingly, if we infer the black body luminosity based on this assumption, then that inferred luminosity ranges between a few percent to a few 10% of the actual bolometric luminosity carried by this SED, because this is not a thermal spectrum. So we think this at least partly explains this so-called missing energy problem in TDEs, as people mentioned. And this EUV emission here, the peak here is really in EUV. I think that can be probed by, maybe the best way to probe them is through these infrared echoes, as mentioned by Megan yesterday. Okay, and also we plotted the ratio between the inferred optical luminosity and the X-ray luminosity at different epochs. And here we just converted them into time, assuming a solar star being disrupted by a 10 to the 6 solar mass black hole. So we can see that if we want to use this to explain this X-ray brightening of optical strong TDEs at later epochs, then the best way to do that is to use viewing angles which are intermediate, like 50 degrees, for example, where we can see initially it's very optically strong, and at a later time the X-ray can catch up the optical fluxes. Okay, so in the last few minutes, I also want to mention a little bit about observations. So very excitingly, we have heard from people, a lot of people, that there are these multi-wave band transient surveys which are just launched or upcoming. Like we have Ruben in optical, Roman in infrared, Ultrasat in infrared, and so on. So I also want to mention the importance of having X-ray transient surveys in this game. So we haven't had a lot of X-ray, we haven't had any X-ray transient surveys since Rosetta until Rosetta came, and then now we have this new Einstein probe transient survey. So maybe some people have heard of this survey. It is a out-scale monitoring X-ray space mission led by the Chinese Academy of Science and jointly by MPE and ESA. So Einstein probe was actually launched already in January this year and is now in commissioning phase. It's expected to be in operation around summer. It has a wide field detection component and also a follow-up telescope. It's designed to find high-energy transients like TDEs, aging variabilities, XRBs, GRBs. We have found a lot of GRBs already, even in the commissioning phase. And I think for particularly the audience in this room, what's the most interesting is that we're going to find a lot of X-ray strong TDEs using this telescope. And especially if we adopt this viewing angle picture, then these X-ray TDEs are going to be found at this angle, which is face-on orientation, for which the optical surveys cannot find them. And I think it's very exciting because we can directly see this accretion power from TDEs and learn a lot of accretion and wind and jet physics in TDEs from these observations. We can study X-ray TDE race and demographics when we have a sizable sample. And also, I want to even mention that we can potentially solve the optical emission origin question in TDEs using these observations. And let me just mention a bit about the last point, which has been mentioned a lot so far in the conference. Right, so how can we use these X-ray detections to differentiate optical emission models in TDEs? So I think people know already there are two main kind of streams of two main models for the optical emissions in TDEs. One of them is post-processing. And in this kind of model, we expected this to set up rather quickly. And then at the peak, we have a lot of obscuring materials. So the X-rays is reprocessed into optical, and we can catch that. At a later time, as just mentioned, we expect X-rays to catch up because of the opening up of the funnel or reducing of the reduction of the reprocessing materials. But also in the earlier phase, before the peak, we kind of expect the opposite to happen, that obscure material should build up, or that superheating wind should build up. So the process may not be exactly symmetric, because in the rising phase, the photosphere, the wind is still just launched and setting up, right? But then we would expect there is going to be some X-ray peak happens first, and then the optical will rise at a later phase, and then at later time the reverse would happen. On the other hand, for the other type of model, we know the optical emission is produced through these outer shocks produced by stream collision. In this picture, the conventional idea is the disk sets up with a delay, right? There's a delayed accretion. So initially, we expect to see only strong optical emissions, and the X-ray is going to pick up only in the later epoch, right? So say if we only have optical transient surveys, we're going to start to see a TDE starting from here. So from here to later time, basically, we cannot use the TDE observations to differentiate these two kinds of models. But say if we have X-ray transient surveys, we can potentially catch this X-ray peak in the earlier epoch. And if we see something like that, I think we can qualitatively say it's more likely possible to be a reprocessing picture than a collision shock picture. So I think I'm at the right time, and let me just stop by this conclusion phase. Thanks.
Okay, any questions? Thanks, Jane. That was great. I had a question about whether the luminosity is actually capped at Eddington in your simulations. There are two ways, I think, that people have discussed getting a luminosity brighter than Eddington. One is just advecting the photons out in a wind, and the other is turbulent transport faster than diffusive transport. Do you see a lot of evidence for that?
So here for the post, I agree that we are not certain about what that luminosity would be. But for the post-processing, we basically just injected some luminosity and see what comes out.
Yeah, I guess I meant in the GR radiation MHD simulations.
Oh, in the GR, yeah, we see more beaming happening in the slower, like in the smaller inclination, right? So if we look at, this is actually the radiation flux. So we see more radiation leaked out here than here. Yeah, but just to say in the post-processing, we actually varied that escape luminosity from Eddington to 10% m dot c square, and the spectrum basically remains quite similar. Just the scale is increasing or decreasing.
Yep. Thanks.
Can you go back to the plot where you had the absorption photosphere in red?
This one?
Yeah, that one. So you mentioned that if then you had a viewing angle that's edge on, then you see optical because you have a larger optical absorption photosphere in this direction. I wonder how the properties of this photosphere relate to the initial condition that you assume, and if they are.
The photosphere relates to what?
How the properties of the absorption photosphere, especially the fact that it extends towards the right, or is that related to the initial condition that you assume?
So this does not relate too much to oh, you mean the disk setup?
Yes.
Right, so yes, so this would relate a lot to the actually this is most in the disk, and we can, for this type of geometry simulations, we cannot evolve them to very far away because the simulation is very slow, right? So in this particular simulation, we've evolved to something around, I remember, like 500 or 800 RG, right? So a lot of this absorption photospheres is in that initial disk setup region, right? But the scattering photosphere, a lot of that is in the wind region, which are launched from the inner disk. And I also want to mention this is a kind of a illustration, and it's assuming a thermal gas condition, but it's actually not thermal, right? So I think all these effective photospheres are just for illustration mainly.
But if the disk was less extended, then you would get less optical.
If the disk is less extended, of course, then every photosphere, the absorption photosphere will cut off here, right? And then the scattering could be a bit more extended as long as the wind extends to there.
Thanks, Jane. So can you go back to slide 16?
16?
Yes, I think. Yes, okay. So if I understand correctly, the third line there means that the luminosity we infer from the black body fit is only 1 to 10% of the true bolometric luminosity because the spectrum is not thermal.
Right.
Can you go now one slide back? So to 50, yes. So I think, how does that work? Because if I look at, if we only have in the bottom plot, the edge on, if I only have the bottom, if I only have the, the optical window, I would imagine the black body that I infer continues, it looks like it's cut out rather than that there's more emission than I would infer from a black body. Right? I feel like if I fit a black body to the optical part, I would get more emission than the real emission.
I think we tried to fit all of them. And if it's an edge-on case, then it's something more like this, right? So it's gonna be a few tens %. And in cases of like this, it's gonna be a few %. So I think there is a table. I don't remember the number right now. There's a table in the paper, like we did the feed to all of the data. Yeah.
Okay, thanks.
Yeah, really cool talk. I'm curious, in the reprocessing picture, for higher mass black holes where you expect the additive ratios to be somewhat lower, potentially, do you expect that more are detectable in the X-rays because the funnel might be a bit wider in general?
I think qualitatively, as the picture is the lower accretion rate in general, and also if you distribute that material around the larger black hole and say if the scale of the wind somewhat scales with the black hole mass, then you have a lower optical depth. yeah, then we would in general expect more X-rays to leak out. Yeah.
So I have a question about the Sedona reprocessing calculation. So why don't you get any lines? It looks like these are all very smooth.
Okay, that's
do
a
you
great
get any
question.
TD helium, TD hydrogen, and so on?
Yes, I think we can resolve the bond-free process here, but then in order to resolve the line processes really well, we need to have higher resolution than these current simulations.
Okay.
So we are carrying those simulations right now, actually, and then we need to also, say, inject some artificial initial broadening of the lines to resolve those, for the code to resolve those.
So you're saying the current calculation does not include bound processes?
We include them, but it's not resolved very well.
Meaning the wavelength resolution is poor at this point?
Yeah.
I see.
So when we can resolve these line processes, we have been seeing some preliminary results. We would see more of the X-rays is reprocessed into UV optical because it's the additional line.
That's right.
Reprocessing.
Mm-hmm. That would be really cool. Yeah.
Okay.
I will be the last person.
Thanks, Jay. So you motivated the kind of accretion rates that are feeding the black hole that motivate your suite of simulations based on the fallback rate. But I guess to get to Clement's point, if we can't run the simulation long enough that we know what's happening throughout the entire disk, how certain are we of the initial conditions? In other words, how the fallback is distributing itself around the black hole. I'll talk about this tomorrow, but I think there's a question, sort of a question of exactly what is, what's the way of saying it, whether we know for sure that adding mass to this envelope from fallback will directly translate into, the accretion rate near the horizon. Mm-hmm. So I guess you have thoughts on how we could proceed in a global context to sort of address this question. In other words, I guess another way of saying it is how, sensitive things would be to the initial configuration of this torus.
Yeah, I totally agree, Brian. So we started from this disk setup, right? So that's already putting a lot of materials close to the black holes already. So I totally agree there is going to be uncertainty in going from that stream collision to the setting up of the disk and how much material gets lost, say, in this collision shock. That's something we cannot resolve in these disk type simulations. One really has to do a global simulation. So hopefully somebody can do that, and we can use their results as a setup to do the GR radiation emission simulations to see what's happening. But also the kind of accretion rate here we have is not that extreme. We didn't go to, say, hundreds of Eddingtons, so it's tens to a few m.dot Eddington.
Thank you.
Sure.
Maybe one more?
Yes, I'm wondering, in the last part of your talk, you talked about how to discriminate optical emission models, and early time X-ray emission is a key signature. And if this one, if I remember correctly, yesterday in Yair's talk, he talked about some in nozzle shock can also produce some early time X-rays in the collision shock scenario. Mm-hmm. So I'm just wondering, maybe in the collision shock scenario, early time X-ray could be produced. So then what could be the smoking gun signature? I mean, is there some specific prediction in the reprocessing scenario?
Yeah, I agree. I think it's hard to say what exactly is going to be the initial emission type in this picture. So we want to see more simulations of the stream collision or these global simulations, right? But then I think we can expect that, right, if this collision shock is very, very strong, and that's going to produce a lot of X-rays, then, the energy of the debris lost radiation, and we should also expect disk to be setting up rather quickly, right? So, if that's the kind of picture, then I think at least accretion should be also rather efficient, and then accretion could dominate over stream collision just because the efficiency of accretion is higher. Yeah, but then yes, more simulations on that along that line would be very helpful. Okay, thank you.
Again.